Okay. Thank you for the introduction. And yeah, I'm going to just fire away. So this is a talk that I've given various flavors over the years, from mostly from my time when I worked with variant medical systems. But since then, some new ideas have developed. Um, so if you look at cancer and you look at the statistics here, this is the number of deaths of people worldwide in 2017, and you see that cancers amount to more than half of the deaths around the globe in a year. Um, the situation in the Western world, for example, Western Europe, where people have better medical care, etc., it's almost equal to cardiovascular diseases, the amount of deaths with cancers. Um, this number will increase because people get older, better health care, so pollution, environment issues, and so they will get more and more cancers as the years go by. If you look at the situation for children between 5 and 14 in Western Europe, you see that 1,200 children die of cancer per year, and it's the leading cause of death in young children. So this is something we want to address and work on. So if you look at the treatment options, you've all heard about surgery, radiation, chemo, immunotherapy, targeted therapy, hormone therapy, stem cell transplant, and precision medicine. This is the toolbox that is usually used and often combined. So people very often do chemical treatment combined with radiation, etc. But today we talk about radiation here in this corner. So if you look at the options, you can radiate people with X-rays. Yeah? And a typical machine like that is shown here, where you have the patient table that can rotate around and move, and you have a rotating X-ray source, so you can radiate the patient from all sides. On the other side, we have protons. This is a proton therapy machine where you have a particle accelerator, a cyclotron. Then you have a beamline that pushes the proton beam up and over into the patient here. The patient is located here on a robotic table again. But if you look at the size differences, so this is roughly to scale if you compare the X-ray machine with a proton machine. And so the proton machines are really big and very expensive compared to X-ray machines. So if you look at radiation with X-rays, you shoot X-rays into a person, and a lot of the dose gets deposited before the tumor, and the X-rays basically blast through your body and do a lot of damage also on the healthy tissue. If you treat a patient with protons are particles that you shoot into a person. When they enter the tissue, they lose energy, they slow down, they lose more energy because they've slowed down, and etc., and they come to a complete stop at a given depth. And what happens is what people call a bragg peak. You get most of the deposited dose at a very defined point in the body. And you can regulate this point by regulating the energy of the protons, and you can move this point and thereby treat the tumor like so. You see that's on the front side, you have much less deposited dose in the healthy tissue compared to X-rays. And behind the tumor, you really have nothing. So for brain tumors and for eye treatment, etc., this is really the only option. And especially for children who have to live the rest of their life with their organs, it's the only option. So you get more localized treatment with these particles. You get reduced damage to healthy tissue, reduced secondary cancers, reduced side effects, improved quality of life. And for children, this is really, I think, the only option out there. However, there are some facilities around the globe, but what you see is that these facilities for particle treatment are not fully utilized. And the reasons are that some doctors still say, oh, are these protons, are they really better? And so for clinical evidence, you need really very large statistics, so you need very large numbers. And since not many people are still treated with protons, it takes a while for that proof to emerge. many people are not aware of proton therapy, so familiarity is an issue. And also because of that, you get limited referrals. If a doctor has an X-ray machine in his hospital, he's not going to refer you to the competing hospital that has a proton machine. And as last point is the insurance. The insurance says, okay, this is more expensive. Should we really pay for that? So all this can be addressed by making these machines smaller in volume, so lower in price, and increasing the number of machines that are out there. So size and cost are really driving market penetration and acceptance. Another picture that shows the advantage of protons over X-rays is here you see a brain tumor modeling. This is modeling of a treatment with X-rays. And you see that the tumor is somewhere here. And you see a lot of those deposited through the entire brain. If you do the same treatment with protons, you see that this area is absolutely not affected, and you really treat mainly the tumor area. And if you compare the difference here, you find that for X-rays, you get an excess of 25 grays of unnecessary radiation compared to protons. So this is radiation in this brain that can cause damage to what, and is completely unnecessary. So 25 gray equals, a lot of CTs, a lot of dental X-rays. It's 25,000 times the annual limit, but the most important part is this: it doubles the chance of getting a secondary cancer. So now this person is treated, and then some years later he develops another cancer in his brain. So if you look at what is installed globally, you can treat people also with heavy ions, which are heavier and therefore even more localized than you can do with protons. But here you see a machine like that installed in Japan. Here's the patient table, and this large thing fits in this point here, and this is the entire facility. So these systems are enormous, and there is another one in Europe, in Heidelberg, in Germany, and here's a person. This is the gantry. So these are enormous systems. For protons, the size goes down if you have a single room system compared to this. What people often do is they have multiple gantries and one accelerator, so you can change the person in one gantry, prepare the patient there while you treat it in another. So you make better use of the expensive accelerator. But still, these dimensions this is almost 100 meters by 30 meters, so it's still large. And if you compare that to X-rays, where you have 20,000 systems worldwide, these are comparably very compact. I mean, you have really, as you increase, reduce the size. This is hundreds of meters, tens of meters. This is meters. You reduce the cost. You reduce everything that is needed to build around it, and you really see that you sell many more systems if you make the systems more compact. Here's a next overview of existing single room treatment solutions. So this is Varian Probium system. Pronova has here a picture I found for a multi-room system. They also move towards a single room system. There is a lot of interest in single room systems because they require less investment. Sumitomo also makes here an accelerator, beamline, gantry. These are cars, so you see these systems remain huge. IBA does something very similar to Varian. You have the accelerator here, the beamline and the gantry here, and then the patient is down here. The only deviating system is actually from Mavion at the moment. They built a compact cyclotron with 913 superconductors, and they mounted it on their gantry, and thereby their system becomes more compact. However, by mounting a heavy cyclotron on a gantry, you still need a big, heavy gantry in a big building. Well, you can study this after my talk in more detail what the market distribution is. So there's you can look at the clinical need for particle treatment, and this is a bit of a complex plot, but I'll walk you through it. So in 2007, you have 12 million annual patients with cancer. This number went up to 17 million in 2018, And the American Cancer Society expects that it's up to 27 million in 2040. If you look at the amount of people from this group that receive radiation is then plotted here. And then you can do some modeling and simulations and say, okay, all these people here would benefit from proton therapy if it were available. And here, the little line here, which is very small, is the amount of people that are actually treated with proton therapy or with particles. At present time, we produce about 15 systems annually globally. And if you look at how much systems this group of patients would need, it's very simply, you have about 300 patients per room per year. You land at numbers that are way, way beyond what is out there. So you see that in 2018, less than 10% of the patients that would benefit from protons has actually access. So if you get cancer, where do you go? Is there a proton center in your neighborhood? And you also see that there's only about 15 rooms created annually. At this rate of growth and 300 patients per room annually in 2040, so that's 20 years from now, there is a need for more than 10,000 extra rooms globally. Yeah? So if you look at this from a business plan, you say, okay, 500 rooms are annually needed more for the coming 20 years. So each year you need to produce that many. You cannot do that with this big system, so you really need to make it more compact. And even if this number is half of that, I mean, if proton would become more available, of course, the amount of people that would benefit, if you have the choice going protons or X-rays, you would obviously choose the protons. So this number might actually be higher even. So what can you do to make this system more compact? You can replace a normal conducting magnet, which has 2 Tesla limit roughly, by a superconducting magnet, and you need a dipole magnet. So if you look at the dipole magnets, the record is about 15 Tesla for a dipole magnet if you use niobium tin. But your magnet technology becomes very, very complex. And this is the beam stiffness. This is how strongly you can bend your protons around the corner with a given field. And you see, as you increase the field, the radius goes down. But at some point, your magnet technology becomes increasingly complicated. So there is some optimum around 7 Tesla, where you gain most of the radius reduction, and the magnet is still relatively simple. But you see that at maximum you find only a 1 meter gain. And so by only switching to a superconducting magnet, you can't gain enough. And there is an example that a study we did at Varian Medical Systems, where you take their Probium 360 system and you replace the normal conducting magnet with a superconducting one. The thing becomes lighter, becomes a lot more compact, but the radius gain is only 0.5 meter. So that's not enough. So you need to do more. So what can you do more? You can look at, okay, now I have a proton beam so in the range of 70 to 250 MeV, which is typically what you need to treat a patient. This is the energy range. And you bend that through a 7 Tesla magnet. You can calculate how wide the beam will be as it exits the magnet, and you find that it's about 70 centimeters. So for the whole energy range, if you push the beam at varying energy through this magnet, you need a 20 centimeter beam tube. However, if you would only pass through this magnet 250 MeV, you can do that in a very small tube. So you can do that basically in a 2 centimeter beam tube. If you then look at, okay, what does that do to the size of the magnet? So here's a very simplistic cosine theta dipole magnet, which is windings that have a cosine theta distribution here, and that gives you a perfect dipole field. It's a very standard textbook example. You find that the field you need is determined by the current density in those windings and the thickness of the winding layer. And the conductor volume looks like so. So from that you find that if you would only pass one single energy through this magnet, your magnet volume, weight, and cost are a factor 10 less. Okay? So if you push only a single energy beam through this bending magnet, you get a very compact and light magnet. So you can make a very compact and light system, but it requires rearranging the system. So we have some ideas on how to do that. So this is, again, a size comparison. This is Varian's ProBeam system, and here is Proton Man, who is a cartoon character that they use at the Children's Hospital. It's the Superman that beats the cancer. But he's 1.83 meters, I think, and this is then what you need to do protons. So if you look at the new system from Varian, the ProBeam 360 system, this is really at the limits of what you can do with the normal conducting gantry. It becomes somewhat more compact, but it's still rather large. Then here you see the Mevion system, where they have put the cyclotron on the gantry, and you see that you still need a box. This is about 10 by 10 by 10 meters inside volume. And you need, of course, thick walls. You need 1.5 meter concrete walls. So in comparison, this is Varian TrueBeam, the typical X-ray system, which is a bunker of this size with shielding walls about this thick. So this is very much more compact than your proton machine. And what we think we can do is we can make a proton system that is by using only the single energy, pushing that through the bending magnet. You could create a system that is this compact. So you would really be able to retrofit this in an X-ray bunker. So your X-ray machine is 20 years old, you need to replace it. You replace it with a new X-ray machine, or you replace it with a proton machine. That becomes an option. There's another way to look at it. You can make boxes that have the bunker volume here and the shielding volume, and you see that really such a system would really be competitive with X-ray. In size, both in size and in cost. You can do the cost calculations on it, and that would be comparable. So again, this is the zoom in on how this X-ray bunker looks like. It's 3.35 meters high, and here's is how a system could fit in there, provided we would make this. This requires a strongly curved superconducting dipole here of about 7 Tesla. And it requires a very compact scanner that needs to be superconducting to make it that compact. So these are two non-trivial technologies that we really have to develop to get there. Then you can ask, okay, if you go just quickly back to this slide, you can see that the existing cyclotron, if you take the legs off, it would already fit there. But ideally, you want a compact cyclotron as well. And this is what I sketched in my cartoons. So if you look at an isochronous cyclotron, its particles enter here, and they are accelerated and circle outward. And you keep them in check by applying a magnetic field from a split pair on the outside, basically. So there's a niobium titanium magnet in this one. And then here are iron pole pieces. And what they do is they wiggle the field like so, along the path of the proton. And what that does is you get focusing, because this beam wants to diverge as it is accelerated, so you need to squeeze it down, and you do that by creating a field along the circumference that looks like so. What happens is that this works the same as quarter poles in an accelerator magnet. It just squeezes on the bundle and makes it stable. So if you want to increase make the thing more compact, you can do that to a certain limit. You think about 5 Tesla, you can make it maybe 2 meters in diameter, but if you go beyond that, you cannot put all the necessary other systems in there. So I think about 2 meters in diameter is roughly the limit. If you do that, for an isochronous cyclotron, this is very specific, an isochronous cyclotron creates a continuous high energy beam, and for treatment that's ideal. Some people use a synchrocyclotron, but then you get beam blobs. You get a discontinuous beam, and that's not so good for advanced treatment where you want to do high energy dose deposition, etc. Another advantage of pushing only the single energy through the beam line is that you get the full energy at the patient. So if you regulate the energy before the bend magnet, you typically lose about 98% of your beam energy before you reach to the patient. So if you want to increase the field, this iron stops working, and you need to create superconducting what they call flutter coils here that do this shaping of the magnetic field. We looked at conductor options extensively. This is what I showed on Friday also in my plenary. So here is the critical current density of HTS conductors and niobium tin and niobium titanium at 4 Kelvin and at 10 Kelvin, except for niobium titanium stops working at 10 Kelvin, so you plotted here at 6 Kelvin. This is a bit of a complicated plot, so but the main thing you see that is if you operate a coil, your current density in the conductor is typically between 100 and 400 amps per square millimeter. So this is why you build magnets usually, and you see that all these conductors are basically sufficient. So to clean this plot up, we go to our 7 Tesla that we need, for example, in our band magnet. And you want to operate this conduction cooled, so at 10 Kelvin or 20 Kelvin, and you see that at that point, the low temperature superconductors are no longer usable. So you really need some HTS, and at the moment, we found that also you can make a cable out of bismuth 2223, which this cable you want to use for the cyclotron outer big coil. And for the flutter coils, you could use just the bismuth 2223 tape. So we selected at that point 2223 for a conduction-cooled compact cyclotron for these reasons. And we then asked Sumitomo Electric to build a coil like that for us. So this is a stack of 6 double pancakes that are connected together. And that was successfully tested at 77 Kelvin at Sumitomo Industries before it was shipped to Varian. And then we asked the University of Twente to put this in their existing EcoSwing conduction-cooled cryostat. This is a big vacuum pot with a big copper plate where you can place this structure to test the coil inside, and then you lower the temperature and you start your measurements. We have made a very complicated clamp structure because you want to control the loads very accurately if you measure this coil. This coil wants to become bigger and wants to deform. So you need some pre-compression to hold it together, and you want that pre-compression to retain as you cool down. So the structure is made to compensate for any CTE difference, etc., to really retain this pressure, and then you can regulate it in a situation as you would have it in your cyclotron. So this flutter coil was successfully tested. The results will be published soon by Twente University. So I come to my summary. You saw that affordable particle therapy, and the highlight here is affordable, can improve the quality of life for millions of patients, and for pediatric patients specifically, it's the only option. These 1,200 children that die in Europe because of cancer should not be necessary. And I'm not saying that protons are the only solution, but at least maybe you can save half of them, and you've done something useful with your superconducting technology. So you also saw that as you can make a business case, this has huge market potential, as they say. So it could be the next big application of superconductivity if it is successful. And it's going to be much larger than NMR, because NMR is small coils. But it's probably still smaller than MRI. But it's a huge market potential that is out there. So you see that it's only possible to make these machines really compact if you use superconducting technologies. It requires some very novel and challenging magnet tricks and system reconfigurations. I think I know how to do this, but this requires money. And that's what I'm trying to find now. And you see that some technologies already have been demonstrated. You can use really, these HTS conductors in a conduction-cooled environment. You coil them up, you test them, and they just work. A compact isochronous cyclotron is not critical for this ultra-compact proton therapy system. You can buy a compact cyclotron, or you can use an existing one in the beginning. Ideally, in the end, if you have a really commercial system, you want a compact cyclotron, but it's not necessary to make this work initially, because a cyclotron is really hard to develop. So that's it. Thank you.
Thank you, Arno. It was very interesting. My question is, can you compare, the compactness that you have shown here that could be reached with the protons with carbon ions? I mean, is it something feasible, or it's not possible to reach this level?
Am I hearing Amemiya-san? Can you hear me?
Yes, I can hear.
Okay, so the question is whether I can compare the size of our very complex system with heavy ion therapies. Yes, I showed some carbon treatment systems, and people are actively working also there on using superconductors and now HTS in Japan especially to make it more compact. But these systems will eventually be larger. There's a big push in Europe by the European Union and in the US to do carbon, because the Japanese have carbon, why can't we have that also? But if you realize how difficult protons are, the carbons are even more difficult. So they're better because they're heavier and they do more damage and they're more localized. But the machine is, let's try and do protons properly first. And that's my feeling.
Noda-san, any question or comments?
I have some one comment. The question: what is the price, cost of your machine? Your goal. What is the goal?
No, I think the price levels are for now in the public domain. There is people often who want to advocate superconductivity for proton therapy often exaggerate these numbers. They claim numbers of 150 million for a machine like that. It's not true. But the real numbers that are out there in the public domain are around 35-40 million, including the building. The building is a substantial part of the cost. Cost almost half of the entire system. If you look at X-ray machines, the investment is about 10 million. So that's really a factor of 5 difference. And I think if we run, of course, the numbers on an ultra complex system like this, we can compete with that. And there has been market research where if you go below $10 million of investment, then you really open the local market at small hospitals. So it's really that level that you need to achieve.
And the cost of 10 million includes the cyclotron and building.
Sorry, the question is if the cost includes the cyclotron?
Yeah.
Yes.
10 million. You say yes. Okay.
Yes, because at currently, if you go to the high-end level cyclotrons like Varian builds, you cannot come to the 10 million overall cost. But if you make a compact cyclotron, then the estimated cost would fit in that envelope. That's how far I want to go on the cost aspect.
Yeah, thank you very much.